All right, that brings us to another topic that's important for experiments and measurements, and that is significant figures. If you took the measurement yourself, you can easily know how accurately the instrument was able to measure it. But if we're looking at values or performing calculations, we're going to need to think about something called significant figures. And this really comes down to whether or not a value gives us more information regarding accuracy or doesn't. Okay, so the first rule of significant figures is that all non-zero values are significant. They're giving us information. For instance, say we measured the temperature of this room to 25.9 degrees Celsius. All three of those values are non-zero, and they all give us information about the temperature of this room. So we say that this number has three significant figures, or 3 sig figs, as it's commonly abbreviated to. Zeros in between non-zero values are significant as well. If we measured the mass of an object at 205 grams, that zero is in between two non-zero values, so therefore it's significant. So we also have three significant figures in this value. That would go in between decimal places as well. We measured the volume of a sample to 2.05 milliliters. A zero is still in between two non-zero values, so it has three significant figures. Zeros at the end of decimal values are also significant. Because they give us more accuracy, they give us more information. So if instead we measured a value to 2.50 grams, that zero is measured, it's giving us more accuracy, giving us the mass of this object more accurately, and so therefore it is significant. So this value again has three significant figures. If this was 42.5050, when we measured this time in seconds, here we have all four of those non-zero values, 4, 2, 5, 5 are significant, so it's 4 so far. The 0 is significant because it's in between those values, and that 0 is at the end, giving us more accuracy. That is also significant, so we have 1, 2, 3, 4, 5, 6 significant figures for that value. So a few more rules before we get to more examples. Zeros at the end, or excuse me, beginning are not significant. Are not significant. So for this scenario, let's look at this value. Say we have 0.025 grams. Of course, the 2 and the 5 are significant, non-zero values. These values, these zeros at the beginning, are not significant. All they really are is placeholders. These zeros are telling us that 2 is in the hundredths place and that 5 is in the thousandths place. So this value only has 2 significant figures. And that will always be the case. Zeros at the beginning of any value are not significant. So here we have a scenario where 3 zeros are in 3 different types of zeros in a value, I guess. So we've got 1, 2 significant figures for the 5s. This 0 is significant because it's in between. This 0 is significant because it's at the end, giving us more accuracy. And again, these 2 zeros up front are just placeholders, essentially telling us the values of this number. And so this is 4 significant figures. Another scenario that you might come across with is values that are larger than 1 that have 0 or larger than 10. And that is a little bit ambiguous, but in reality we wouldn't count them. So zeros as placeholders are not significant. What we mean by that is, let's say we have a value of 1,250 kilometers. We've got 1, 2, 3 significant figures there. That 0, well, as it's written now, we're not sure if it is significant or not. We'd need more information or write it a different way. For right now, we would say that this is just 3 significant figures. That 0 is essentially just a placeholder. So how would we get rid of that, or show that that 0 is significant for that 1,250 kilometers? That would take us to our last rule, and that is scientific notation. All values in scientific notation are significant. Okay, so we'll talk about scientific notation first, and then we'll finally work through some more examples. Okay, so scientific notation is essentially a way to talk about really, really big numbers or really, really small numbers very conveniently or efficiently. Okay, so in all scientific notation values, so here's an example of scientific notation. So it's 1.0 times 10 to the third milliliters. That's how we would say that. 1.0 times 10 to the third milliliters. Okay. All scientific notation values have a decimal part. And in standard scientific notation, you only have one integer and then the rest decimals. And then we have an exponent part. So what the exponent part is telling us is, basically how small or large this decimal part is. This exponent part can either be positive or negative, and that's how will tell us whether it's large or small. If the exponent is positive, that means the value is larger than 1. And what you do is you're going to take that decimal part and multiply it by 10 for however many times that exponent tells us to. Okay, so let's take this number, 2.5 times 10 to the third. What that's really telling us is that we're going to take this 2.5 and multiply it by 10 3 times each for each exponent. So times 10 times 10 times 10. And if you threw that in your calculator, you'd equal 2,500. If the value is 1.1 times 10 to the fourth, we would multiply that 1.1 times 10 4 times. And that would give us 11,000. If the exponent is negative, that is telling us that it is a number smaller than 1. For instance, let's say we had a value of 3.5 times 10 to the negative third. What's that telling us is to multiply 3.5 times essentially 10 to the minus 1 3 times. And 10 to the minus 1 is the reciprocal of 10, or 1 over 10, and we're going to multiply that 3 times. And if you take 3.5, multiply it by 1 over 10, times 1 over 10, times 1 over 10, we'll get a value of 0.0035. If we have value of 5.67 times 10 to the negative 2, we're going to multiply that 5.67 times 1 over 10 twice, or 0.0567. One thing that we'll have to be able to do is interconvert between those two values, between scientific notation and standard values. Pretty easy to do that, converting it to standard values. Just you can use your calculator. But to convert standard values into scientific notation, we can use a couple tricks. Basically, moving the decimal values. So let's say we want to take this value, 45,235, and we want to put it into scientific notation. What we're going to do is we're going to find the decimal place, which is right there, and move it. And we're going to count how many times we move it. If we move 1, 2, 3, 4, that's the exponent for our value. So we moved our decimal to right there for standard scientific notation, 4.5235 times 10 to the 4th. Since this was a bigger number than 1 and we moved the decimal to the left, it has to be a positive exponent. If we have a number less than 1, we can convert it to scientific notation in the same manner. We're going to count how many times we move the decimal place. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that becomes our exponent, but since it's less than 1 and we moved it to the right, it is a negative exponent. And that will enable us to talk about especially larger values with different numbers of scientific notation, or excuse me, significant figures using scientific notation. So say we had that same value, or that value we were talking about before, 1,250 kilometers. We said that 0 wasn't significant, or at least it's a little ambiguous. If we wanted to display it as a significant figure, the best way to do so is to put it into scientific notation. So we're going to count 1, 2, 3, and that would become 1.250 times 10 to the 3rd kilometer. And that 0 there shows us that its value is significant. So this would be 4 significant figures. If we had a value such as 100,000, and we wanted to display it in 3 significant figures, we would have to take that approach as well. We would say that this is 2, 3, 4, 5, 1.00 times 10 to the 5th, whatever value this was measuring. This scenario, putting things in the scientific notation, also gives us a really good proof of why zeros at the beginning of decimal values are not significant. We had this value, 0.0000217. When we converted it into scientific notation, all of those non-significant zeros at the beginning went away. Why? Because, well, now the information that they supplied is in the exponent part, telling us how big or small this value is. Okay, so let's do a couple more examples and try to figure out how many significant figures these values have. Okay, so say we looked at a measure that was 215.20 grams. Okay, how many significant figures are on this value? Okay, we know all non-zero values are significant. That 0 It's at the end, so it is significant. So this has 5 significant figures. What about a value like this, 0.00215 seconds? Okay. Well, we know those 215 or 0. That 0 at the end, excuse me, is significant. The zeros at the end, beginning aren't. And so this is 1, 2, 3, 4 significant figures. What about 1.010 times 10 to the negative third liters? Okay, these numbers are all in scientific notation, so they are all significant. So this has 4 significant figures. Another thing we're going to have to be able to do with significant figures is perform calculations and report our answers to the correct number of significant figures. So there's a couple of rules that we're going to have to apply. There are rules for addition and subtraction, and then there are rules for multiplication and division. The rules for addition and subtraction is that the answer must be reported with the least number of decimal values as the calculations. Essentially, we have to be conservative in what we are saying with our answer. It also will make a little bit more sense with our multiplication and division rules. Okay, for multiplication and division, the rule is very simple, or very similar to positive or adding and subtracting, and that the answer must be reported with the least number of significant figures as our calculations, or calculated values would be better. Okay, let's see this in practice. All right, first we've got a problem with an addition and subtraction. And so let's throw this into our calculator. All right, so 3.45 plus 4.5 minus 1.234. That gives us an answer of 6.716. But that is not the correct answer when taking into account significant figures. Okay, so our rules for subtraction and addition are that we have to report our final answer to the least number of decimal places as our calculated values. Okay, for instance, this value 4.5, we only know whatever that measured value is to the 10th place. We don't know any information of it to the hundredths place or thousandths place, so we can't report this value past the 10th place, and that's why the rule is there. So this has 2 decimals, this value has 1 decimal, and this last value has 3 decimals, and so we have to cut our answer down to 1 decimal. So everything past that 1 decimal has to go, and so we're going to cut this down to 6.7. Now that 1 was less than 5, and so we rounded down or stayed the same. And we'll talk about more of those rules once we do this next problem. Okay. So let's do B. All right, so this is a multiplication and division problem, so we're going to take 4.0 times 2.5 divided by 0.752 equals quite a big set of numbers. So we got 13.29 7, 8, 7, 2, 3, 4. So for multiplication and division, we have to count the number of significant figures in our calculation. So this one has 4.00, 3 significant figures. 2.5 has 2 significant figures. And then this one has 3. That 0 at the beginning is not significant. So again, we have to be conservative in what we say about what we know. This answer, as we wrote it down now, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. There's no way we know this value, whatever his measurement is, to that degree of accuracy. We only know this second value to 2 significant figures. So we have to cut it down to 2 significant figures. So everything past the 13 has to go. And so we're going to cut this down to 13. Let's say, for instance, though, that this was 13.2978, 7, 2, 3, 4, and we had to cut it down to 3 significant figures. Okay, we'd want to keep that tenths place, but in doing so, we're going to cut down this value, and here's we can talk a little bit more about rounding rules. If the value we're cutting off is greater than or equal to 5, we are going to round up. If the value that we're cutting off is less than or equal to 4, we're going to round down or stays the same. Okay, so in this scenario, when we had to cut it down to 2 significant figures, that 2 was less than or equal to 4, so we kept it the same, 13. If we were cutting this down to 3 significant figures, that 9 is greater than or equal to 5, and so we're going to round up, and so that would be 13.3.